begin, you have 12 minutes, and then 3 minutes for questions.
Okay, all right. Well, I'll try to zip through things. I couldn't find a good picture of the Moon and Mercury together, so let's see. How do I switch through slides? Play. Oh. All right, so I made one there. Okay, so this is work with a bunch of people. Paul Lucy has done some great recalibration of the LOLA laser reflectance data set recently with Miriam Lemlin, his student, and then Greg Newman with the laser altimeter from Mercury. And we'll try to go on a wild ride here. I probably have too many slides for 12 minutes now I'm thinking about it. Essentially, so we have a laser altimeter on Mercury. And Mercury, we have really strong evidence of surface ice from a bunch of different data sets now. And we have a very similar instrument on the Moon. And it's now recalibrated to the level that we start to believe the reflectance we're getting from it. And then I'm going to talk to you about the theory of how we can summarize all this in what's essentially spectroscopy as a function of temperature rather than a function of wavelength of a measurement. Then what do we see in the LOLA data and how do these compare? And then if we get a chance, we'll talk about the LAMP data as well. Okay, so these are the big questions we're trying to get at here. Is do we see any similarity in the laser reflectance between these two bodies? And are we seeing some evidence that the same volatiles might be on each of these bodies? And I think that really strengthens the argument if you're claiming that something is a volatile that's giving this indication on Mercury, and you believe it's water there, then this really strengthens the argument that you're seeing water on the Moon, if you see it in the same place. And then what does this tell us about the sources? So this was sort of our current understanding from the page 2013 paper about Mercury. You can see that as a function of temperature, the average laser albedo brightness actually does this crazy dance, right? And we use this as evidence for there being surface water, that when you hit 100 K, the surface suddenly started getting brighter. So there's, so 100 K is the temperature where ice should last sitting on the surface for geologic times. So billions of years, it won't go away. And so that seemed pretty consistent with that story. But then the question is, what are all these other features going on? Like up here at 150 K, why do we have this big dip? What we postulated in that paper was that there might be organic materials left over from comets. So that actually is telling us not only that there's water ice, but it's also telling us something about the source material. So we're going to try to push this technique to see how much we can get out of it. So here was the MLA data at the time of that paper. Now the MLA data, because they did a big off-nadir campaign, they've really filled in the polar hole, and so we can push that a little further than we did in that paper. And then here's the equivalent data set now for LOLA. This is Paul Lucy and Miriam Lemlin's new reflectance. We got new diviner temperature maps now that are really good. And we could basically look at the surface and try to figure out, okay, at this temperature, if this volatile, say here's water, right? We say it should be stable at about 100 Kelvin, right? If it's going to be there, then what would it look like? What would we expect? And what would we expect from each of these different volatiles? So water ice starts to be stable at 100 K. Well, what does that actually mean as far as what we should expect for the surface brightness? Well, you should start to get these little micro cold traps like Paul Hayne was talking about earlier, maybe 20 K warmer or something, right? Because our model and the diviner measurements are at a much larger spatial scale, right? So there might be subpixel stuff that's 100 K, even if you're measuring 120 K. So you might expect the surface to start to get bright a little above your stability temperature. Then if you go too far below it, your material basically acts not as a volatile, but as any rock. And so micrometeorite erosion will get rid of it. And so you expect a peak. And so this is where I start to say, okay, maybe this is like a spectra, right? Because we have a spectral line, a spectral band for any volatile as a function of temperature. Then you can imagine there are things that are going to affect this. If you have a thicker volatile, it might withstand the impact, the micrometeorite gardening a little longer. And so you would spread out those peaks. And so you're actually telling something about the thickness of your material as well. Likewise, if there's a volatile that darkens the surface instead of brightens it, normally we think of water ice as brightening the surface, you might get a dip instead of a peak. So now you can think of this, this is now the full MLA data set, including that polar hole. So now we've gotten temperatures well below 100 K from some really cold polar areas. You could start to use this crazy idea to try to map out the volatiles that you're seeing on the surface. So here we see at 100 K we start to get brighter, right? And it starts around 120 K or so, so there's probably micro cold traps on Mercury. And then as we get colder and colder, we get brighter and brighter. So the question is, can we use these diagnostic of different volatiles? Here's a bunch of volatiles that I'll get at a little later in some of the other slides. Well, here's what we see for the moon. Right? When we do this nice recalibrated data set, what do we see? Well, right at 100 K, we suddenly get a nice brightening. Okay, so I think this is pretty good evidence that we're seeing surface water frost in a lot of places in the moon. This is from the South Polar data set. And then we see bumps and wiggles all over the place, just like we saw on Mercury. And so what information can we pull out of these? Are we seeing other types of volatiles in here? Just to go over, here's the two data sets compared to each other. Take-home message here is Mercury is pretty dark and has a lot more contrast than we see on the moon. And here's just to show you what this actually means as far as brightening of the surface. So on the moon, we're getting things that are up to 10% spatial area mixed in with some white material, assuming that ice was pure white on the surface. You'd get that. Here's the same thing for MLA data. You can see it's substantially darker than the average surface. So even though we have some ice that's very near the surface, the average spatial coverage of that is quite a bit darker. Okay, so take-home message: Mercury is dark. Brightening doesn't really require all that much coverage either, though. So here they are together, and let's just go through some of the possible volatile features we're seeing. All right, first of all, they both get brighter at 100 K. I think this is pretty good evidence that if we believe that this feature, this rise here, was caused by ice on Mercury, then that feature there is probably caused by water frost on the moon. So we're able to use an instrument like this to potentially map out water frost. You can see maybe other bumps are coming out at lower temperatures. So you could claim either that's like some different form, a thicker layer of water frost on Mercury, or maybe you're seeing evidence on both of them of sulfur dioxide or carbon dioxide are volatiles that would be appearing around those temperatures. All right, but you don't see this, you see a constant rise on Mercury, and you don't see that sort of thing on the moon. So that's telling us something different about these two bodies. Now this might be pushing it a little, but here you see at about 150 Kelvin, they're both getting a nice little bump. Right? It's not something as bright as the water frost feature, but this is something that you might call a spectral feature. And it seems to happen at the temperature that naphthalene would form. It seems to be a sensible thing that you would expect there. It's the simplest PAH that you could imagine collecting on the moon or Mercury. Better known for its use in mothballs. All right? So we found evidence of mothballs on the moon and Mercury is what the conclusion of this talk should be. Yeah. So we're not going to find moths on moon or Mercury. That's what and then you can look at other features. So some of these dark organics that we were postulating on Mercury, you saw a dip around 150 to 200 K. You saw other dips around 300 K. And we don't necessarily see evidence of those. So if those are some sort of complex organic or some sort of complex sulfur molecule, right, that we're trying to figure out that we can identify here, I suggest coronine could cause darkening at this level. Anthracene could cause darkening around these temperatures. We don't really see the same evidence for those complex organics on the moon. So that, again, might be telling us something about the source material. And that actually goes pretty well with some new stuff from Megan Brooksall about the different sources of mercury being more dominated by micrometeorites that could carry more of these volatiles than the moon. Okay, so let's go. So they both show signs of water. They show evidence for other types of brightening. They maybe both show simple organics, but Mercury seems to be the only one to show complex organics. Then another thing to strengthen this argument that we are actually mapping water frost is to do a comparison with what Paul Hayne recently published in the volatile special issue of Icarus, was the lamp brightness as a function of temperature. And you can see that that same feature at 100K is really showing up in both the laser altimeter and the lamp, and then there are a few features that don't necessarily match. And so this is great. We have like 4 spectral bands now of mapping the frost on the moon, and maybe we can get more with a new mission. I'll go over that. Let me just skip to this here. So this is sort of now, Paul had this map of the lamp possible detections of water frost. Here's sort of my best current map of where Lola could be detecting water frost. So now we have to start to compare and contrast these two. And then, yeah, just to go over a little bit, so you might see like, oh, well, a lot of the, we know that Shackleton is around 100K. And Maria Zuber published a paper years ago about, oh, Shackleton is bright because of the geology, there's something special there. But just to show that these measurements are robust, even if you take out Shackleton, cut a little hole in your map, you're still seeing this general brightening. So essentially, we're seeing evidence for water frost, brightening on both Moon and Mercury, possible organics, and that the lamp doesn't show some of these features, but maybe it shouldn't. Maybe at those wavelengths you shouldn't expect these features. So just wanted to throw that whole idea out there, and maybe we can get some good progress going on that. So thanks.
Okay, we have time for questions.
So we know that there's argon in the exosphere of the moon, and that condenses out on the night side of the moon. So have you looked for an associated feature with argon in the poles?
No, I haven't. Do you know what sort of temperature it starts to condense around? Is it?
I think it's in that same paper.
Argon? 20, about 20, yeah.
Okay.
But it does condense on the night side. So, I mean, for short terms. I mean, not billions of years, but.
Okay. Well, Ben Greenhagen has been looking at the temporal aspect of some of this, so that might be a good candidate for some of the. He has potentially seen some differences in the daytime and nighttime data. The only issue as part of that recalibration is to take out a lot of the daytime data, because that's giving you an extra signal that might, so reflected light might look the same as your laser, so it's not necessarily totally separable from the time of day.
One more quick one.
Matt, have you, Michael Poston, Caltech. Matt, have you thought about what your detection limits might be if these temperatures pan out? Like at what minimum concentration of water you'll see brightening of the soil?
I guess it depends how much contrast you hope you could get, but I don't know. Yeah, going back there, maybe 1% or 2 you would need coverage. Thanks.